Yesterday afternoon was too. But at least we got a little bit of sun coming in now. That might warm us up just a tad. I doubt it much, but it'll help.
Yeah.
But not much. Okay. What we've got first, well, let me mark the roll. That's going to take a while. 237. All right, that took a while. Now, I think we were at the bottom of page 15 in section 1.2, if I'm not mistaken. Any questions on anything we've done so far? Okay. All right. Had we done example 3? I guess we. Example 3. That's just a,
elementary row operations. Yeah, we did some of that.
Yeah, I think we got that done, but I didn't have time to tie it in with what came next. So let me just basically write down example 3. We're not going to do it all again, but we started with a linear system. Let me get my pen set up. Okay. Nope, it's not. There we go. X minus 2y plus 3z is equal to 9. Yeah, this is one we've done in several different forms already. Minus x plus 3y equal negative 4. And 2x minus 5y plus 5z is equal to 17. Okay. Now, we wrote that first as an augmented matrix, which became 1, negative 2, 3, 9, negative 1, 3, 0, negative 4, 2, negative 5, 5, 17. Yeah, I remember doing this now. Okay, and then we proceeded to do row reduction. Okay, so this became 1, negative 2, 3, 9, 0, 1, 3, 5, and 2, negative, well, let me go on and do the next step too, rather than writing down so much over and over and over again.
What operation did you do to the second line again?
Let's see if I did it right. Yeah. Add the top row to the second row.
Okay.
So that gives you the 0, 1, 3, 5. Okay. And the next one is minus 2 times the top row plus this one. So that's the 0 and minus 1, minus 1, minus 1, I think it was. Okay? Now, that was operating with the first row on the second, then on the first row with the third. Then what we got left to do is operate with the second row on the third. Just add those two together. And that finally gave us this. 1, negative 2, 3, 5, 0, 1, 3, 5. Yeah, whoa, that's a 9, not a 5. I knew something looked wrong there. I can't read my writing. Okay, and then adding the two bottom rows together, you get 0, 0, 2, 4, right? Now, one last step is divide the last row by 2. So you get 1, negative 2, 3, 9, 0, 1, 3, 5, and 0, 0, 1, 2. Okay. Now, That's where we ended last time. That's where we stopped. I wish I had had the foresight to hold you a few minutes longer and say, this has a special name. This matrix here is what we call being in. Now, what we were doing was row reduction. Okay, that was what we were calling that. So this is called row echelon form. What does that mean? Here are the three requirements for row echelon form. The first non-zero entry in every row is a 1.
Oh.
Okay. Secondly, of course, now that really incorporates that, means everything under a leading 1 is a 0.
Cascade the lines.
Yeah,
Right.
and then, and the third is that the 1s go to the right and down every time. Now, you may have wound up, this one didn't, you may have wound up with, say, if you had another row in here and this didn't have but this turned out to 0, then that would still be row echelon form.
Okay. So it doesn't have to be perfect.
It doesn't have to be a perfect diagonal there, but the first non-zero entry has to be a 1. The 1s have to step from left to right, as you go down, and 0s underneath the 1s. Okay. Now, that said, that's what, on the bottom of page 15, if you got that on your thing, row echelon form, and then we'll also introduce what we call reduced row echelon form. So the row echelon form is this one. Matrix in row echelon form has the following properties. Now, I didn't say this one. If you had wound up with a row that all became zeros, that has to be at the bottom. And that could have happened anywhere. As soon as you have one, move it to the bottom. Okay, I forgot to say that one. So that's number 1. Any rows consisting entirely of zeros occur at the bottom of the matrix. Now, if that would have occurred in this one, that would have been okay. Okay? If you would have had, since this represents the system of equations, if you would have wound up with 0, 0, 0, 2 here, that's not okay.
Yeah.
Because that would have said that 0x plus 0y plus 0z is equal to 2. And that
Which is a no solution problem right off the bat.
How's that?
Which is a no solution problem right off the bat.
That's it, exactly. But if it's all zeros at the bottom, that's fine.
Yeah.
That means you're probably going to have infinite number of solutions. Not necessarily, but it could. Okay?
They're all reals.
Yeah. So, but this one worked out just fine. Okay, so that's the first thing. Any rows consisting entirely of zeros, move them to the bottom. Number 2, for each row that does not consist entirely of zeros, the first non-zero entry is a 1. For every row that isn't all zero, and sure enough, we got it here.
We can have multiple 0 rows, right?
Yeah, if you had multiple, they'll all be at the bottom. But then the first non-zero entry in any non-zero row has to be a 1. And those are called leading 1s. And then the last is, for 2 successive non-zero rows, the leading 1 in the higher row is always further to the left than the leading 1 in the lower row. Or the one in the lower row is further to the right than the one in the upper row. However you want to say that. Now, one other slight change to this is row echelon form. From now on, I'm going to call it RE form or something like that. I don't like writing row echelon. There is another form called reduced row echelon form.
So RE.
And what you do there is, for the leading 1s, don't just put zeros underneath them, get zeros above them as well. Okay? And you see how you do that? Say this row, using this leading 1, go up to this one, multiply this row by 2, add it to this. See, that's not going to change this one because that 0 equals 1 is 0. It's 1 still. So that doesn't lose that. But that becomes a 0 then, and then you do it for the others too. And then this one, once you've done it for that one, then do it for this leading 1.
So a perfect reduced row echelon form would have nothing but 1s and 0s.
Yes. Okay. Well, remember, you could have another row in here that had an entry here but a 0 here.
So it can still be reduced.
Yeah. It's just all the 1s have to have zeros above and below.
Okay.
The leading 1s, even though if you had a few that skipped, had extra zeros
Because I guess
here.
you couldn't, there's nothing, no operation that you could reasonably do that would produce zeros in that final row.
Yeah. So, now, the thing with reduced is not only the leading zeros have to have zeros, leading ones have to have zeros under them, they have to have zeros above them.
Okay.
That's the thing. Now, if that were this problem, which it could be,
I can
and
already
we'll
see
do
why
it,
that is
then,
useful.
yeah,
Because you get
X equals that, Y is equal this, Z is equal this.
I understand.
You already got this. Right
Well,
now,
so-
you have to back substitute.
That also explains why that last row will usually not cleanly be zero.
Right.
Because it would be in a
Well,
row number.
yeah. Pretty, that's it. So, that's row echelon form. If you had zeros above those two leading ones, that -2, the 3, and the 3, if you had done the row operations to make those zeros as well, then you would wind up with reduced row echelon form. Okay? Now, row echelon form is basically the same as Gauss elimination when you're just dealing with eliminating things here.
Right. 'Cause
You
you've got
go
one
down
row-
and then you do back substitute.
You've got one row now that you know the value of this.
Then you can back up and get the others. Now, if you have reduced row echelon form, that's called Gauss-Jordan elimination. Jordan went the extra step and got zeros above those, and that made all of life
Reveal
easier.
itself, basically.
Yeah.
That's great.
So,
I can't imagine how big the discovery that must have been.
yeah. But before the times of computers that would do big ones like this, that was sort of just an interesting mathematical thing. You know, now it can really be powerful. So let's do example 4. Hopefully this is a different problem. They use the same ones over and over a lot. So let's clear this and do example 4. Oh, no, this is multiple. Okay. It says determine whether each matrix is in row echelon form. Row echelon, not reduced, row echelon form. If it is, determine whether the matrix is in reduced row echelon form or not. Okay, so here's the first one. Example 4a is 1, 2, -1, 4, 0, 1, 0, 3, and 0, 0, 1, -2.
That would be row echelon.
Row echelon form, not reduced. Okay?
So
All right.
some work to do. Although it does reveal 2 of the variables.
Yes, it does, because of that second 0 in the second row. Exactly. But you still have to do some back substitution to get the first variable. You're absolutely right. Okay, here's B. 1, 2, -1, 2. 0, 0, 0, 0. And 0, 1, 2, 4, -4.
B isn't, but you do a row swap and make it row echelon.
You got it. It's not in row echelon form because that row of zeros is not at the bottom. But like you said, if you do a row swap, then it would be. Wouldn't be in reduced still, but it would be row echelon form. But with the row of zeros there, it's not. You're right. Okay, here's C, a bigger one. 1 minus 5, 2 -1, 3, 0, 0, 1, 3, -2, 0, 0, 0, 1, -4, and 4 zeros and a 1.
Row echelon, not reduced.
Okay, definitely row echelon form, and as you said, not reduced. Now, this has a lot of caveats in it. If this represented a 4x4 set of equations, and these were your constants, okay, then the first thing, no solution, okay, as you pointed out already, these would all be zeros. But let's imagine that was a 0 there, you had a 1, 1, or something else here. No, you didn't have that. It was 0, 0. Okay. This would be a variable without a leading one, so that would have to have a parameter. You have, if this is 0, 0, that's fine. You have, what is this, x1, x2, x3, x1. x4 equals -4, x3 you can calculate from that, x1 you can sort of do, but you have to put a parameter in t or something like that to do x2, because there's no way to solve for that.
Right.
Because that 0 there
it
has
has no independent.
Right, exactly. No leading one. Okay. So, but that didn't have to represent that, but if it did.
Can you also describe the first two variables like a relationship as well?
Well, yeah, the first two would both have the T in it, the others wouldn't have a T in it. Yeah, right, exactly. Okay, so there's C. Let's do D. 1, 0, 0, minus 1, 0, 1, 0, 2, 0, 0, 1, 3, and 0, 0, 0, 0.
This is the reduced.
Say again?
This is a reduced row echelon.
Yeah, it is row echelon form because row 0 is at the bottom, first non-zero entry is a 1, and all the 1s step over 1. And it's also reduced row echelon form because all the leading ones have zeros above them.
And it actually has a solution because that last row is all zeros and does not break the identity of
Yeah. If this represented a system of equations, then you would have more equations than you needed because you have four equations, 3 unknowns. Obviously, one of those equations either is not going to work, which would give you no solution, or
really
it's not
nasty
necessary.
problem. Is it reduces to that, but then the final row reduces to a 1 on the end to give it a no solution?
Yeah, then the whole thing would be a no
Yeah.
solution. Because
Even though it reveals the value of all of the variables, it still can't be solved.
exactly, because that fourth equation didn't fit the other 3.
Yeah.
So it was inconsistent. This one, like you said, this would show the fourth equation was dependent on the other 3, so that's why all the zeros became there. And then you, like you said, that would solve, and you'd know right what x equal -1, y is equal 2, and z is equal 3. Piece of cake.
Specific coordinates would be the intersection of those 4 planes, wouldn't it?
Yeah.
Yeah.
But the fourth plane would have been coincident. Well, it wouldn't have to be coincident with, yeah. I think it'd be coincident with, well, yeah, it could be any plane, but it would be a linear combination of the other planes. And, but it would go through that same point. It wouldn't be, introduce something else. Now, for it not to be, these will always do at this point, and this would be down here somewhere. That would be a no solution.
Right.
Okay. Now, E. I don't know if I've got room. I'll try to write it here small. 1, 2, -3, 4.
Yeah, the last 2 or 3 rows.
0, 2, 1. Okay, what did you say?
So just in the last 2 problems are 3 rows. They probably
Yeah.
just fit.
Okay. 0, 2, 1, -1, and 0, 0, 1, -3. Whoa. What about that?
We do not have a row echelon because we have a leading 2
Yeah, that is the one thing that keeps it from being row echelon. Okay.
Probably a fairly easy way to reduce it.
What's that?
Probably a fairly easy way to reduce that row down to.
Yeah, divide everything by 2.
Yeah.
You have 0, 1, 1/2.
Yeah.
Painting that with the fractions, but it then would be row echelon. Yeah. Okay, but that in that form is not. And then this one is sort of an interesting one. 0, 1, 0, 5. 0, 0,
Yeah, it is.
1, 3, and all zeros.
It's a row echelon, but it gives us absolutely no idea what that first parameter is.
Yeah.
Or if it even is important at all.
Yeah.
That first parameter could have no correlation to the rest of the system. This is all 0.
Yeah, and another way to say that, you could plug in any value you wanted to, and it wouldn't change the rest of it, which is a bizarre
That's
part.
basically the definition of no correlation.
Yeah, exactly.
Yeah.
Right. So there's, it's fairly there's a word for it, and I can't think of it now, it's flying into, not a well-posed problem, you might say. It's a bit bizarre. If this did represent a system of three equations and three unknowns, then this one was completely dependent on the other two. Z is equal to 3, Y is equal to 5. And by the way, this would be reduced row echelon form as well. It's row echelon and reduced row echelon. Still, I'm telling you about it. And Y would be 5, and X could be T. Any value at all. And the others don't depend on it. It doesn't depend on them yet. Absolutely.
It must be along a, well, yeah, it must be along a, the planes are along the origin. When one plane is 0. Oh, I can't remember what it's called. And it's perpendicular to the origin in some
right.
way. I can't remember what they call it.
And I mean, I can't even imagine a set of equations that would come out to be.
Yeah. Because
if you had any variable to begin with, you'd still have the variable.
Right.
And so it's kind of strange. We'll just leave it there.
To the X.
What's that?
It must be perpendicular to some plane on the X axis.
Right. Yeah. And to have absolutely no X dependence whatsoever. Yeah. Okay. So going to the next little box after example 4, and I'll clear all this. You don't need it any longer, do you?
No.
Okay. All right. Gaussian elimination with back substitution. I don't know why they say this again now, but here's what you would do. This is called Gaussian after, goodness gracious, I can't think of his first name. Gauss. Huh? Huh?
I can't think of him either.
Yeah, I think we had him here. It's not Leonard, that's Euler. It's not Johann. Goodness, what is his name? Such a great mathematician. Carl Friedrich Gauss. Right. I knew he was in here. Gaussian elimination with back substitution. Okay, I'm going to abbreviate that. So, what's the rule? Okay, you're given a system of equations. Write the augmented matrix. Okay, write the augmented matrix of the system of linear equations. Number 2, do your elementary row operations to rewrite in row echelon form. That gets you into row echelon form. Okay, elementary row operations, just getting ones where they belong, zeros below. That's all you do. Not reduce row echelon form, just elementary row operations to get it in row echelon form. Okay, and then write the system of linear equations corresponding to that row echelon form. So the first step was take the system of equation to a matrix, then you do the elementary row operations on the matrix to get it in row echelon form, and then take the matrix back to system of equations. And that would involve your parameters if you have them, evaluating if you don't. And then you'll see. So the middle part of the alphabet's doing okay. The top and bottom missing completely. Okay. So, and you do that using back substitution. Write the system of equation corresponding to the matrix in row echelon form. Use back substitution to find the solution. So this is where the back substitution comes into play down here. All right. Now, if you're into applications, this book does a pretty good job of mentioning these. You know what GPS, okay? What GPS is doing is solving systems of equations.
It's actually really, the satellites broadcast the time down to the nanosecond
Wow.
all the time. And then your GPS takes 5 of those and solves using the speed of light and the angular velocity of satellites to find the distance to those 5 satellites. The Air Force has a math equation that tells it exactly where those satellites are at any given time. It checks against that and knows exactly where, or you get 2 points. 1 point is on the surface of the Earth, and 1 point is at the edge of the coverage in space. And obviously, unless you've got the special GPS chip that allows it to track in space, it will be on the surface of the Earth that I was looking for. So when I was at UAH for 2 years, we were having our space hardware club. We got one of the GPS chips that works in space. To get it, because we were making a CubeSat at the university, I worked on the batteries team. So I worked pretty closely with the team that was doing the guidance control. The guidance control team had to go through training for what they call ETAR, which is a less severe version of ITAR security, the security for military projects, and for anything space related is considered an advanced weapons technology, so that they mandate strict security. And in order for us to get one of these chips, the military had to sign off of it, and it had to be delivered under armed guard to our lab, which had to be secured, to the team lead, who basically had to sign that he would protect it under penalty of treason and all this other stuff. It was insane. I got to see this little chip in the armored suitcase. This little chip could guide a missile very easily. And we were about to stick it in this satellite. It's like a $15,000 chip just sitting in our lab.
And what the signals, like you said, are coming. You have to have a minimum of 3. Mm-hmm. Usually you'll have more than 3.
It's 5 for the precision of the GPS within a meter. Mm-hmm. Any more for even finer measurement than that.
Yeah. And your system of equations are based on the data you get from that, and calculating what the distance was, the times, all those things go into it.
Even relativity, you have to take into account that the signal's delayed because of the velocity of the satellites relative to the surface of the Earth.
Right. So you need several inputs to be able to account for all those variables. Okay. And so you have to have at least that many. So sure enough, but that's linear algebra.
Yeah. That's what our guidance, navigation, and control team, which was all graduate students, was solving. Mm-hmm. All the undergrads we were all on the structure and the power and all that stuff. Yeah. The graduate students were all simulating the GPS system and computer models and stuff like that. Yeah. Crazy.
All right. So let's do this Gaussian elimination method with back substitution to a new system. I don't think we've run into this one before. I don't think we have anyway. Maybe, but let's see. Here's a system of equations. First one starting with x sub 2, and here's Justin. Okay. We're on page 17 in section 1.2. X sub 2 plus x sub 3 minus 2x sub 4 is equal to negative 3. X sub 1 plus 2x sub 2 minus x sub 3 is equal to 2. 2x sub 1 plus 4x sub 2 plus x sub 3 minus 3x sub 4 is equal to negative 2. And the last equation, x sub 1 minus x sub 4 minus 4x sub 2 minus 3x, I can't read, minus 7x sub 3 minus x sub 4 is equal to negative 19. And they seem to like to do this. They go along fairly reasonable looking numbers until they get the last equation, put a big number there. I don't know. The last couple of them have been like that. I can't get my pen back. Okay. That's x of 4. First step. What?
Put it in an augmented matrix.
Exactly. Now, I'm going to cheat. Is that okay?
Yes.
Because I don't want to write the whole set of numbers down twice. So what's the next step would have been? Just picture that as a matrix. Okay, that's what we're going to be doing. Which would be the first one we would do? Yeah, we need some. We don't ever want to start off with a 0. Okay? Okay, unless they're all going to be zeros. Okay, that example we had earlier. We need to have a leading 1 here. So we're going to either need to move row 2 up here or move row 4 up here. Okay? I think it's easier to do 2. So I'm going to do that as my first step. Both write it as an augmented matrix and swap those first 2 rows. Is that okay? It's cheating, I know, but it's all right. So the new first row will be 1. You tell me.
We're doing line 2, right?
Yeah.
So 1, 2, minus 1, 0, 2.
Okay. Next.
So starting with row 3.
Now I'm going to do row 1 now.
Line.
No.
0.
0, 1.
Then 1. Then another 1. Then negative 2. Then minus 2.
Okay. Now the next 2 are easy. And okay, make fun of my writing. I'm not hurt by it at all. I'm just fine. It's a minus 4.
Yeah, minus 7, minus 1,
And minus 19. That's just 6. Okay, and when you do it in matrix form, be sure you put your brackets around it. Okay, so we've done the first step, which is get it as augmented matrix, and we've done the first row operation, elementary row operation, which is swapping the first 2 rows. Next. What's the next thing you want to do? Anybody? What's the next thing you want to happen?
do some more operations to try to reduce it down to reduce echelon.
Okay, and what will that involve? What will be the next operation? What you want to see happen?
Divide 2 by 2.
Second? Yeah, you want that 2 to become a 0, don't you?
Right.
Because you got a 1 there, 0 below it, that came with it, and then you need these 2 to become 0. So we'll do whatever row operation will make that a 0. What would that be? Yeah, you use the top row. Use that leading 1.
Okay. We could subtract twice the top row.
Okay, yeah, that's right. Negative 2 times the top row plus the third row. Okay, that's it. Negative 2 row 1 plus row 3. That's exactly what you said, only you said it in slightly different order.
Yes.
So you leave the top row alone, 1, 2, minus 1, 0, 2. Like I said, there's a lot of tedium here, writing down the same things over and over. The second row you leave just like it is, 0, 1, 1, negative 2, negative 3. Okay. Now the new third row will be do that operation on the top row, on the third row.
So that would be 0.
It better be a 0, okay? Zero again. Yeah. Next. Say again? Don't think so. minus 2
Oh,
times,
minus 1 times minus 2. So that would be a minus. Is that going to be minus 1?
okay, minus 2 times minus 1.
Oh, yeah. 3.
3, got it. Okay. All right, next. Negative 3. And next. Isn't it negative 6? Negative 6. Okay. Now, what's the next operation? Elementary row operation.
Divide that row by 3.
Okay. Later we'll do that, but let's get this one taken care of.
Alright, so we can subtract the top row
From the fourth row. So it's minus row 1 plus row 4. Okay? And that will give us
0,
0
minus 2,
minus, wait, minus 6.
and then minus 6.
Yep. And
And 1,
negative 1.
and then minus 20.
Yes. It's minus 21, isn't it?
Oh, yeah, it's 19.
Okay. Negative 21. Okay. Now, I like your foresight and thought on this. Yeah, let's divide that row there by minus 1. I mean by 3. Yeah, 3.
So
Okay.
it'd be
To make it
minus
1 minus 1 minus 2. Okay. It looked like we were going to do it here too, but those didn't agree at the end. Okay. Now, I'm real tempted. No. Okay. We can do that as we go. I think that'll be fine. Okay. Now, but let's think about get back into our order of things, okay? We flipped the 2 rows so you have a leading 1. You wound up with a 0 under it, we created 2 more. Now we look at the first non-zero entry in row 2, which is already a 1. Fantastic, we wanted that. Now we want zeros below that. Since this is just row echelon form, we don't need to reduce, so we don't need to go above. Okay, well, we got a 0 there, we need a 0 there. So, let's do that. Now, normally what we do is write down the first row, write down the second row, and write down the third row. And we're going to write down the first 2. 1, 2, minus 1, 0, 2, and 0, 1, 1, negative 2, negative 3. But rather than writing down row 3, which we're not operating on now, let's do what you suggested and divide. So I'm going to do row 3 divided by 3. Okay, so it'll be 0, 0, 1, minus 1, minus 2. Now we'll do the operation on row 4. Okay, and that would be, what? Okay. Am I in the right? Yeah. Using row 2, how do we get this to be a 0? Six times row 2 added to row 4, right? Aggravates me. Itching right there. Okay? 6 times row 2 add to row 4. Well, 6 times 0 is 0 plus 0 is 0. That stays good. We don't want that to change. Okay? 6 times 1 is 6 minus 6 is 0. That's what we wanted. So proceed from here.
Oh, I see. We need to do both operations
Yeah.
together.
6 times 1 is 6. Another 0. How nice. And then we have a 6 times negative 2. Negative 12 minus 1 is negative 13. That looks like a pain in the neck, but let's see what happens next. 6 times negative 3 is negative 18 minus 21. Goodness gracious. 39, minus 39. Hey, that ain't too bad. Okay. Because what do we do now?
You can reduce that row.
Yes, how?
13's prime, isn't it?
13's prime. By what?
Oh, is it divisible by 13?
Yes, divide by negative 13.
Yeah, very nice.
Divide by negative 13.
So, yeah, so that should be minus 1 and minus 3.
No, divide by minus 13 to lose the minus.
Oh, yeah, so 1 and 3.
Yeah. 1, 2, minus 1, 0, 2. 0, 1, 1, negative 2, negative 3. 0, 0, 1, minus 1, negative 2. And 0, 0, 0, 1, 3.
So you had to
Got it.
construct that last number to be so high so that it would be obvious that there's nothing else to divide it by.
Okay. Or they were just being obnoxious. I don't know which. Okay. Now,
Start messing with double-digit prime numbers. You can get large very quick.
right. We've done our row echelon form now. This is row echelon form. For those who came in late, this is the definition. If you had a row of all zeros, it has to be at the bottom. We don't, so we're fine. Then for every non-zero entry in each row needs to be a leading one. And sure enough, we have that in all 4 rows. And, of course, everything below that has to be zeros. We have that. And the leading ones step to the right as you go down
You don't step over by 1.
These happen to step over by 1. You wouldn't have to have it. You could have had a number in there. It just wouldn't be 1. Okay, so we got it. So now we can do our back substitution. Where will we begin?
We'll begin at the bottom.
Right. And remember that the 4th column represents x sub 4. So we know right now that x sub 4 is equal to 3. Okay?
Now we just plug it into the next row.
Right. So I'm going to come over here and do that. Let me, for right now, get these extraneous marks off the page. I made them for some reason, maybe by mistake, but I still must have made them. Okay.
That would be x sub 3.
So x sub 3
Or actually, x sub 3
minus 3 is equal to minus 2. So what would x sub 3 be?
1.
X sub 3 equal 1. Add 3 to both sides, and you get x sub 3 equal 1. Okay? The next one gives us x sub 2, that one,
1
plus 1
minus 6.
minus 6 equal negative 3.
So that flips that to a positive 3 once we move the 6 over.
Okay, say that one more time.
The negative 3 should become plus 3 once we move the 6.
Okay, but you still got the 1 there.
Right.
So that would be
the 1, and that takes it down to
2. So x of 1 is equal to 2.
That's x sub 2, is it not?
X of 2, sorry, you're right. X of 2 is equal to 2. Let me just say, yeah, because you could do it this way. That'd be x of 2 minus 5 is equal to minus 3, add 5, and you get 2, yeah. And then the final is x of 1 plus 4 minus 1 equal 2.
So 2 becomes 3, which is over, and minus 4, so minus 1, so x1 equals minus 1.
Okay, x1 equal, you said negative 1? Yeah. Because this becomes a plus 3, and when you subtract it, it's minus 1. Perfect. Okay? Now, it's not impossible, but it does get a little tedious. Let's check and see if it's right. 2 plus 1, that would be 3, minus 6 would be negative 3, or no, that's negative 3. Negative 1 plus 4 would be 3, minus 1 would be 2. That's right. Okay? Negative 2 plus 8 would be 6, plus 1 is 7, minus 9, negative 2. Yes, that's right. This one's going to be a little bit of a pain, all right? Negative 1 minus 8, that would be negative 9, minus 7, minus 16, minus 3 is minus 19. Yes. So sure enough, those four values are the one and only solution to that system of equations. All right, good deal. And they got x of 1 equal negative 1, 2, 1, 3. Got it. Well done.
Could that set of four that be a three-dimensional problem plus a parameter?
What's this again?
Could that be like a three-dimensional graph plus a parameter with time for t or something?
If you want to think of it that way, that certainly is
I was thinking
trying to apply.
4x4.
Yeah.
Other than the obvious multi-dimensional graph.
Yeah. But as we'll see later, linear algebra isn't restricted to real life. You can have multi-dimensional space. Now, the thing is, you see, these don't have to represent. There is a way this could represent, in a sense, not in that form, but that same matrix could represent polynomials of different degrees. It could represent matrices of, it can represent just about anything. We'll hit this in one of the last chapters we do. The matrix can represent just about anything. And you're not limited to 3 dimensions in that. Or even
the idea of recursive matrices is very
well, just like we said, GPS, you could have several signals coming in. Right. So you're not limited to, So those X's don't have to be links. They could be just almost any number of things. All right. So what we've just done is Gauss elimination. That's reducing its row echelon form and back substitution. All right. Now we're going to look at another example, a little bit shorter, thank goodness. This is 4 equations, but only 3 unknowns. So here's what this one is. X of 1 minus x of 2 plus 2x of 3 is equal to 4. X of 1 plus x of 3 is equal to 6. 2x of 1 minus 3x of 2 plus 5x of 3. All right, here's this. Now the top part of the alphabet is here in great force, 4 out of 4. The bottom 3 are missing completely. Okay. Now I think Muhammad was telling me that he would be out today. He has something with work or something that he wasn't going to have to be here. We're doing example 6 on page 18. Equal 4. I didn't finish writing down that equation. 3x of 1 plus 2x of 2 minus x of 3 is equal to 1. Now, what we've been doing before you got here is taking systems of equations and solving them using Gauss elimination, okay? Which means we take the system of equations, first step, write it in as an augmented matrix. Then we start reducing that augmented matrix using our elementary row operations. There's 3 of them: exchanging rows, multiply one row times another, or multiplying a non-zero value by any given row. Those are the 3 elementary row operations, trying to get the matrix into what we call row echelon form, which, to review that, if you wind up with a row of all zeros, that goes at the bottom, and the first non-zero entry in every row is a 1, called a leading one, and underneath those leading ones are all zeros, okay? And those leading ones in step from right to left, downward, okay? Left to right, downward, okay? So let's first get this as a, what's your first step? Write it as a N. Help me, somebody. Anybody? It would be a matrix, an augmented matrix. And what would that be? 1, -1, 2, augmented would be 4. Okay, next. 1, 0, 1, 6. Next. 2, -3, 5, 4, and last. 3, 2, -1, 1. Done. Okay, now what's the next? First thing you want to happen with this matrix, you want that first entry to be a 1. It already is. We don't have to do anything to make it 1. Okay? So we're fine. What do you want to happen next? Zeros below the 1. All the leading ones need to have zeros below. Okay? So what we're going to do is what? What would be your next step? How do you make this 1 into a 0? Draw a circle around. No, that won't work. Remember the 3 elementary row operations? Exchanging 2 rows, that won't work. Multiplying by a non-zero constant, that won't work. So it's adding a multiple of 1 row to another row. That will work. What do we need to add? Using the leading 1 up here in the first row, what we need to do? Negative row 1 to row 2. That will do it, won't it? That will make this one a 0. Okay? So, write down the first row. You're using that 1. 1 minus 1, 2, 4. Okay, what does the new second row become? 0, -1. Second?
0, -1, 0, and 5.
Okay, I think, okay. That next one is going to be -2 plus 1 is -1, isn't it? Is that what you said? So minus row 1 plus row 2. Okay, so -1 plus 1 is 0. Minus and -1, oops, I messed that up. That's a +1, sorry. Maybe that's what you were saying. Okay, but then the next one is going to be -2, -1 times 2 is -2 plus 1 is -1, right? Okay, next. Second? I can't hear. Did you say 2? Yeah, okay. All right. Now, what do we want to happen next? That 2 needs to become a 0. So what we need to do to make the 2 a 0? Using the top row, that leading 1, negative row 1, -2 times row 1, plus row 3. Right? That'll do it. So what will that give us? 0. -1, right? Okay. Then you get 1. -4. Perfect. What you want to happen next? The 3 needs to become a 0. How do we make that happen? -3, row 1, plus row 4. Time out a moment here. I want to give you a big hint here if you haven't noticed already. Since we're working with leading ones only, okay, to get this to become a 0, do the opposite of this times that plus this. And that works. -1 times this plus that. Yeah. The opposite of this times that. -2 times this plus this. That will give you a 0. The opposite of this. -3 times this plus that. Works every time. That's how you choose what your multiple is, and then you add. And it does. It works. Okay? And what does that give you? 0, 5, -7, is that right? -7? Okay. And -11. Boy, that last row is looking weird, isn't it? All right, now what's the next thing you want to happen? Let's review. You got a 1 there. It was already there. We're fine. Get zeros below it. We got them. Then what's the next thing we want? We want a 1 there. We got it. It was already there. Good. Okay. And now what do we want? Zeros below it. Okay. Now, to make that happen, we're going to use this leading 1 here, and it's pretty obvious what you do with, and you want zeros below it, so to make this one a 0, pretty obvious, you just add those two together, right? Okay, so write down the first row, 1, -1, 2, 4. Remember, a lot of redundancy here. Write down the second row, because that's where your leading 1 is. 0, 1, -1, 2. Now, operate on the third one. Row 2 plus row 3. What do you get? Row 2 plus row 3. 0, 0, 0, right? -2, right? Hold the presses. As soon as you write that down, you see we have a problem all day. Because remember what this stands for? These first 3 columns stand for your variable, the coefficients of a variable. So what we have here is 0x1 plus 0x2 plus 0x3. What's that add to so far? 0 is equal to -2. When's the last time 0 was equal to -2? Never. It can't happen. So as soon as you see this, stop and say, no solution. No solution whatsoever. No way that can happen. It doesn't matter what happens with that 4th row. Thank goodness. I didn't want to mess with it anyway. But you stop right there and say, that can't happen. There's nothing you can do to undo it. It just can't happen. Okay? And they basically did the same thing. They went on and fiddled with it. They just wrote down the 4th row again because they knew nothing good was going to come out of it. Okay. So that's what we call Gaussian elimination with back substitution. Here we didn't have to do any back substitution because we knew it wasn't going to work. No way that could work. Okay? But now we're going to do Gauss-Jordan elimination. Okay, now remind me, we don't have much time, but let's see if we can get this done. Okay. Well, let's just stop here before I erase this page. We were doing Gaussian elimination, which is, get it in row echelon form, which is leading 1, zeros below it, leading 1, we were trying to get zeros below it until we ran into the snag there. And then the next would have been a leading 1, zeros, yeah, that's what we're trying to do. That's row echelon form, and then you do back substitution. Okay? Now, what we're going to do, and that's called Gaussian elimination. What we're going to do next is Gauss-Jordan elimination, which involves reduced row echelon form. And here's the difference. Bless you. Okay. I think we're awake now. Okay. Yeah. All right. With reduced row echelon form, here's what we do. Just like before, we want a 1 there, zeros below it. We want a 1 there, and zeros below it, just like we were going to do, but now we also want zeros above it. So zeros both above and below your leading ones. Okay? And that's the difference in Gauss-Jordan elimination and Gauss elimination. Gauss elimination got me doing it. Okay, we're competing with each other. Okay. Now, I think you got confused with that. Okay. You want zeros above and below. That's called reduced row echelon form, and that leads to Gauss-Jordan elimination. Because then, basically, all you have to do is write down your answers. You don't have to do back substitution. You still may have parameterization, but you don't have back substitution. So let's see if we can do one quickly. I don't know if we can or not. Carl Friedrich Gauss is still the Gauss, and Wilhelm Jordan is the Jordan part of it. And if you go back and check, Jordan lived a century or more after Gauss did. So they didn't ever collaborate. They were not ever alive at the same time, but he took what Gauss did and extended it. So here's where we'll start. X minus 2y plus 3z, I think we've seen this before, is equal to 9. Negative x plus 3y is equal to negative 4. Yep, I know we've seen this one before. And 2x minus 5y plus 5z is equal to 17. He sure is conservative with his values here. Uses the same one over and over again. First thing we're going to do is write it as a matrix, augmented matrix. So what will that be? Help me.
1 minus 2 plus 3, 9.
Next.
Minus 1, 3, 3, 0, negative 4.
Next.
2, negative 5, 5, 6.
Okay. Okay. First thing we want, once we have the matrix like this, we want that first number to be a 1. We got it! Already, we didn't have to do a thing. What's the next thing we want? A 0 below it. In fact, both zeros below it. So, to get that, we're going to leave the first row alone. 1, negative 2, throwing things at me. 3, 9. Okay? Huh? All right. How do we get the negative 1 to become a 0? Not negative. Plus, you just add them. The opposite of this, which is that. Yeah, so that'd be 1, yeah. Row 1 plus row 2. That'll make a 0 there, won't it? So what does that give us? 0, 1, 3, 5. Okay? Next thing we want is a 0 beneath that. So how do we get that to happen? Negative 2, row 1 plus row 3. The opposite of this one plus the top. Okay? So that will give us what? 0. Second? Negative 1. Negative 1. Second. One more time. Not quite. Negative 1. Negative 18 plus 17 is minus 1. Okay? Or you're doing minus 16. No. Okay. All right. Now, so what's the next thing we want to happen? We got 1 here, 0 is below it. Next we want a 1 here. We got it already. But this time we want zeros above it and 0 below it. So we're going to operate on the top row using the second row, that leading one on the second row. So what will we do? 2 times row 2 plus row 1. Okay? So I'm using row 2, so I'm leaving it alone. 0, 1, 3, and 5. Okay? Now, do the operation you just told me. 2 times 0 is 0 plus 1 is 1. We didn't want to change that. Then we get 0. That's exactly what we wanted. 9. Next. 19. Boy, these are getting big numbers. Who wants to do this anyway? Okay, what do we want to happen next? The minus 1 below it to be a 0. So how do we make that happen? Row 2 plus row 3. Perfect. That's easy. What does that give us? 0. That's good. 0. That's good. 2, 4. Okay. Now what's the next thing we want? Let's review what we got. We wanted a 1 here. We had it. We wanted zeros there. We got them. We wanted a 1 there. We had it. We wanted a 0 there and there. We got them now. And what's the next thing we want to happen? First non-zero entry in each row to be a 1. So how do we make that 2 into a 1? Nah, don't do that. Remember your 3 elementary row operations? 1 exchanged 2 rows we didn't need to. The one we've been using, multiplying a multiple of 1, adding a multiple of 1 row to another row. That's what we get to zeros with. How do we get 1s? Okay, yeah, I guess you maybe could, but that's going to mess up other things. What you do is just divide by 2 or multiply by 1/2. Multiply by a non-zero number, 1/2. And that will do it. So this will be, I like, rather than say multiply by that, I like to say R3 divided by 2. That to me is just as simple. Okay, so leave the others alone. 1, 0, 9, 19, 0, 1, 3, 5. Goodness, my writing stinks, okay? And then this one divide by 2, 0, 0, yeah, 1, 2. Perfect. Okay. Now, what's the next thing we want to happen? We got our leading 1 here. We want zeros above it. Ooh, this is going to take some effort here. Not much, but so what do we do first? You're going to use this 1 to try to make that a 0. How will we do that? Negative 9. Yeah, let's do this one first. Negative 9, row 3 plus row 1. Okay? Now we're using row 3, so write it down. 0, 0, 1, 2. Okay? Using that row, operate on the first row. Negative 9 times 0 is 0 plus 1 is, we didn't want that changed. Next, negative 9 times 0 is 0 plus 0 is 0. Why? We didn't want that change, and it wasn't. And negative 9 times 1 is negative 9 plus 9. Ha! That becomes a 0, just what we wanted. Now the bad news. Negative 9 times 2 is? Negative 18 plus 19 is? 1. That's not bad. Okay. And what do we want to happen next?
Then we want to get row 1 above and row 2 to 0.
Yeah, we wanted that 3 to become a 0. How do we make that happen? Using row 3. Negative 3, row 3, plus row 2. Got it. And what will that give us? Negative 3 times 0 is?
0.
Plus 0 is?
0.
Good. We didn't want that to change. Then negative 3 times 0 is?
0.
Plus 1 is?
1.
And that we didn't want to change. Good. And then we have negative 3 times 1 is? Negative 3 plus 3 is? 0. That's exactly what we wanted there. And then finally, negative 3 times 2 is? Negative 6 plus 5 is? Negative 1. Okay. Don't go to all this work and get a sign error. Okay? Don't. Yeah. This is too much work to make a sign error at the very end.
I'll be using my calculator doing it.
Okay. So what do we have here? And look, here's the advantage of Gauss-Jordan elimination. What do we have? X equal 1, Y equal negative 1, Z equal 2. 1, 2. There your answers. No back substitution required. Just write down the answers. Now, occasionally you'll have a missing column there or something that you have to have a parameter in, but at least for this, it's easy. Now, as I said, we've seen that one before. If you flip back to example 3 on page 15, you'll see that our solutions were 1, negative 1, 2, but that one we did with Gauss elimination, back substitution. You ought to get the same answer we did. Okay. Now, I think we're out of time, right? So we can't do any more. We're going to need to start next time with that little thing at the bottom, which is a pain in the neck, okay? But we do need to start there. So that's where we'll begin next time, okay? And that's at the bottom. But let me give you a few homework exercises first. I know you don't want to leave home without that. And these will be any of the odds 1 through 5, either 7 or 9, any of the odds 11 through 17, any of the odds 19 to 23, and any of the odds 25 through 37. I think you may even be able to do 39 if you want to. It's long and difficult, but you can do it. And we'll stop there and pick up the rest of them later. Okay?
Hey, Dr. Fowler, yeah. I'm not guaranteed to miss that, but I'm literally moving.
Oh, wow.
I moved into my new unit on the 29th, and so I'll be starting to gather stuff up. So if I'm not, because we have, the one I'm in now ends on the 31st. So I got like 2 to 3 days to kind of get everything cleaned and get everything out. So that'll be, and then I take you on every day.
Right, I see, yeah, I know.
So if I'm not here,
Right.
that'll be my reason for why. Right. But I still like check.
Yeah, follow it on this. And like I was telling them earlier, last night in my physics class, I forgot to turn on the recorder. I was just going along, and at the end I went to turn off the recorder. I said, where is it? And it wasn't there. So always, if you're here, make sure I've got that running. Okay, good deal.
You had it running yesterday.
Yeah, I did. Yeah.
All right, thank you.
All right, good deal. Have a good move and a good weekend.